Alright, since translational equilibrium is so much like something you already know, I can't let you get away with just learning that in one night. So tonight you're also going to learn how to calculate friction. Instead of just labeling it on a free body diagram, you're actually going to be able to assign a number to it now. So here's the formula for calculating friction. The force of friction is mu, that's the Greek letter mu, times the normal force, which you may have come to know as Fn. N is also an accepted symbol for it. So let's go through these. Ff is the force of friction measured in newtons, so that could be confusing because now there's a bunch of n's all over, measured in newtons. The coefficient of friction is mu, and coefficients are unitless numbers. So you'll deal with other coefficients in physics. That means that they have no units, which also means they don't make any sense by themselves. They have to have something with them. And that's something that goes with the coefficient of friction is the normal force, also measured in newtons. So the force of friction is mu times the normal force. There are two mu's that we'll use for friction, and my slide is for some reason formatting them wrong. So that's written incorrectly. Mu subscript s, little s, is the coefficient of static friction, and this applies to objects sitting still. So static means at rest, applies to objects at rest. Mu k is the coefficient of kinetic friction. And the word kinetic means moving. So the coefficient of kinetic friction, mu k, applies to objects in motion. And a handy fact of the universe is that static friction is always bigger than kinetic friction. And you can test this right now by grabbing an object, setting it down on a table, pushing on it until it starts to move, and then keep pushing and move it at a constant velocity. So don't speed it up, don't slow it down. What you'll notice is you had to push harder to get it to start moving than you did to keep it moving. And that's what static friction bigger than kinetic friction means. It's harder to get something moving than to keep it moving. All right, let's dive into some math now using that information. All right, this first example is going to be kind of long because I'm going to explain to you what everything means as I go. What is the minimum horizontal force that will cause a stationary, it's going to be important, stationary 10 kilogram block to slide? Assume that mu s equals 0.2 and mu k equals 0.1. So remember on the last slide I told you that mu s, static friction, applies to stationary objects, things that aren't moving, and mu k, kinetic friction, applies to moving objects. So for this problem, because the block is stationary, we don't need the kinetic, because we want to know how much it would take to start it sliding from rest. And how much force it takes to start something sliding from rest is exactly what the equation from before, using static friction, can tell us. So if you ever want to know how hard you have to push to start something from rest, you have to balance out friction to get it moving. You have to balance out static friction to get it moving. And you might just think when I say that, oh wait, if I balance out the static friction, doesn't that mean that the forces are then zero? Yes. But physicists realized that when they came up with the coefficients for static friction, and they said, let's write the coefficient for static friction so that if you balance this coefficient exactly, you'll start something moving. So this is like the one place where physicists kind of violated their own rule of we're going to write static friction coefficients so that balancing them starts something moving, even though the forces are then balanced. And I'm doing air quotes as I say balanced in that case. So force of friction when you use static friction's coefficient will tell you how hard it is to start something moving. So it's force of friction equals mu s times the normal force. Now, how do we find that normal force? Well, we know the object's mass, and we know that it's obviously sitting somewhere if we're going to get it sliding. So I'm going to say this is a 10 kilogram box. All we know is it's an object. We need to find its normal force, which is the support force from whatever it sits on. But we don't have enough information to do that directly. However, maybe we could do this as a static equilibrium problem. So this box, in addition to the normal force, also has its weight pulling it down, force of gravity. There aren't any left and right forces involved in finding the normal force, and so even though I'm going to push on this thing, and that will cause a force the way that I push, right now I'm concerned with the normal force, and that's an up force. And when I'm dealing with up forces, they have to balance down forces.
Wait, what kind of forces?
Up forces, Mr. Thopper. So up forces balance down forces. My up force is my normal force, and my down force is my weight. I don't know my normal force, but I can use the object's mass, remember Fg is m times g, to find its weight. 10 kilograms, 10 newtons per kilogram. I got sloppy. So my weight is 100 newtons, therefore my normal force is 100 newtons. And since I've been using big N up here in this equation, normal force. Okay, so now I'm ready to find the minimum force to start something moving. Force of friction is mu s, I know that, 0.2, and it's unitless because it's a coefficient. Coefficients are unitless. Times the normal force, 100 newtons. 0.2 times 100 is 20. So, minimum force required to start that object moving is 20 newtons. Now this question was asked in a really convenient way. It says, what is the minimum horizontal force to start something moving? So the minimum means you can just say, oh, well, it has to be at least 20. However, most problems will say, what force would start this box moving? And in that case, you have to set this up as an inequality. So instead of just saying it's equal to 20 newtons, you say any force bigger than or equal to 20 newtons will cause that box to move. Any force bigger than or equal to, any force bigger than or equal to 20 newtons will cause that box to move. Alright, next example, which hopefully will be a little shorter now that we've got the basics down. Next example. If the coefficient of kinetic friction between a 35 kilogram crate and the floor is 0.3, what horizontal force is required to move the crate at a steady speed across the floor? Okay, so we're looking at coefficient, oh, I meant to grab my pen, not move that around. We're looking at coefficient of kinetic friction, so we know at some point we're going to use mu k, between the 35 kilogram crate and the floor, okay? And we know the coefficient of kinetic friction is 0.3. Coefficients are unitless numbers. What horizontal force, that's an x force, horizontal is x, is required to move the crate at a steady speed across the floor? So upon reading this, you might think, okay, so we're looking at balanced forces, maybe this is a equilibrium problem. But ultimately, if you're just looking at the force it takes to move something at a steady speed, that's the force of friction using the coefficient of kinetic friction, mu k, because we're moving it at a steady speed. And we want to balance then the force of friction when it's moving. Force of friction when something is still is bigger than, or can be bigger than, I should say, can be bigger than the force of friction when something is moving. So we're going to use Ff equals mu k times the normal force. Once we've balanced this force of friction, all of our left and right forces will be balanced. So if you think about a crate moving to the right with some velocity, that crate then has the force of friction resisting it. And if we want to keep that box moving at a constant velocity, we have to balance that force of friction with some kind of push. So solving this problem will tell us how big that push has to be by telling us how big the friction is. So once we know the friction, the left force, we'll also know the right force. Okay, Ff equals mu k times n. Finding the normal force is the same as before. We know that the normal force will be equal to the object's weight. If you're confused about how I concluded that, look back at the last example. So Fg is m times g, so our normal force is the weight of this object, which is 35 kilograms times 10 newtons per kilogram because we're on Earth. Normal force is 350 newtons. Okay, now we're ready to fill it in. Force of friction equals mu k, 0.3, times 350 newtons. Force of friction is 105 newtons. Therefore, to balance the kinetic friction, we must apply a force of 105 newtons. So, the crate was moving, we wanted to keep it moving at a constant speed, we have to balance the frictional force. Kinetic frictional force, so we use mu k because it's moving, kinetic, moving. And when we find the force of friction using mu k, we then know we have to push just that hard. Alright, final example. Final example, hopefully this one will go quick now that we've got the basics down. A force of 48 newtons is required to start a box moving across a horizontal concrete floor. So if we had to start the box moving, that means it started out not moving. So we're obviously dealing with static friction, not kinetic. So we're going to end up using mu s, coefficient of static friction. All right, keep going. To start a 5 kilogram box moving across a horizontal concrete floor, what is the coefficient of static friction between the box and the floor? Okay, so once we've balanced, air quotes, balanced, the force of friction on this object, we will start the object moving. So we're dealing with the minimum force required to start an object moving, and that is the force of friction using the coefficient of static friction. Okay, and so far I've been saying the force of friction using the coefficient of static friction. Starting in class tomorrow, I want to shorten that to there's static friction and there's kinetic friction. And just know that the one from static, you used mu static, mu s, and the one for kinetic, you used mu k. And this little fish symbol means is proportional to, so it means that mu s is related to this force of static friction, mu k is related to the force of kinetic friction. I'll remind you of that as it becomes important. Maybe I actually just shouldn't have interrupted my example. So if that confused you, let's come back. What is the coefficient of static friction? So we're solving for mu s. What is the coefficient of static friction between the box and the floor? Okay, so they gave us our force. This is FF. So FF, our force of static friction, is going to be 48 newtons because whatever that person had to push had to balance static friction, and so they had to push 48 newtons, meaning they balanced another force of 48 newtons. Left forces equal right forces. We have a 5 kilogram box, so we can find its normal force. Up forces equal down forces. Normal force is up. Normal force on a horizontal surface counteracts force of gravity. Normal force, therefore, is mass times gravity. Normal force is 5 kilograms times 10 newtons per kilogram. Normal force is 50 newtons. Alright, so I'm going to find mu s. Let's go ahead and solve this equation for mu s. Divide by the normal force on both sides. Now I have my force of static friction divided by the normal force is mu s. If I sub in, I get 48 newtons over 50 newtons equals mu s. And if I divide 48 by 50, I get 0.96. Remember, coefficients are unitless numbers, so there we are. Whatever that surface is, it's really rough. It took 48 newtons to move something. It's a big force compared to the thing's weight. So you almost had to push as much as the thing weighs to start it. It's an interesting problem. Kind of curious about what that surface is. Maybe it's like a really rough sandpaper. All right. Hopefully you can do these examples, and I hope that throwing in this kind of language and using the proportional to symbols didn't throw you off. If you need to rewatch this example and maybe ignore that part, that's fair. But that's friction, and that's how you calculate it. Pretty straightforward. Hopefully this unit's going a lot easier than kinematics. All right, see you tomorrow in class.